Hello and welcome everyone to today's webinar. Our subject today will be measuring dynamic torque. But before we jump in, and for those who are not familiar with us yet, I want to give you some background of who we are at Mountz. Mountz is a family-owned company that was created in 1965. Since then, we expanded and our headquarters are still located in San Jose, California. Our main distribution and warehouse facility in Foley, Alabama. And we now have our international sales and service center just out of London in the UK. Mountz as a company has always been 100% focused on torque, whether it's through the manufacturing and sale of torque tool to apply torque, or also tool to measure torque. As such, we were the first company to manufacture an electronic torque analyzer in the early 70s for a famous defense company. Our customers operate in many different fields: medical, defense, automotive, electronics, and aerospace being among some of them. As of me, I'm Adrien Auger, Technical Sales Manager with the international team. Through my 10 years experience, I've been able to travel to many different places to meet our customers and help them overcome the assembly challenges they were facing at that time. And this gives me some good tools to help our customers today throughout their process to meet their expectations and requirements. Going back to today's subject, which is measuring dynamic torque. Every company dealing with assembly and having torque tools on their production line should have in place a measuring torque policy integrated into their quality management system. The reasons are very simple, is to make sure that the quality is reached. The two main issues of not having such a measuring torque policy integrated are the first being that it's possible to over-torque the assembly. So over-torquing is basically applying too much torque on the fastener, which in turn will create too much tension into the assembly. And this will eventually result in the parts breaking or the parts deassembling and then creating quality issues. The other way around is under-torquing an assembly. So in this case, we don't apply enough torque onto the fastener. So there is not enough clamping tension, clamping force into the assembly. This also will eventually result in the part deassembling and in quality issues. So having a measuring torque policy is really creating an added value onto the assembly line. There are two main ways of measuring torque, and those are static and dynamic torque measurement. Static measurement is going to be basically a reaction measurement. So we are going to use static sensors to do that, and we are going to basically check what is the torque output of the tool. Whereas with dynamic torque measurement, it's really a dynamic version of checking the torque, measuring the torque of the tool. And this will allow us to take into consideration different variables that are important when checking torque tools. This is especially true with power tools, as those power tools come with more variables than hand tools in terms of torque application. The most important variable with power tool is going to be the rotation speed, as we all know, power tools, so air, electric screwdrivers, will turn a lot faster than any hand tool. And this rotation speed will create some inertia when the target torque is reached by the tool, which in the end will play on the torque value that is being applied on the assembly. Other variables can be locking nuts that will possibly turn into lubricants, or the parts themselves, if it's, as an example, with gaskets or rubber joints, rubber seals. This elasticity will absorb some of the clamping force and some of the torque applied into the assembly, and this will eventually play also on the torque being delivered on the assembly. There are other parts that can be variable, such as really the material of the parts themselves. If it's steel on steel, it will be a very hard joint as well, but also other variables such as thread cutting screws that will impact, once again, the torque delivery. So measuring dynamic torque will be able to take these variables into consideration and then adjust the tool to make sure that the torque delivered on the assembly matches the requirements and expectations. So what is a rotary torque sensor, also called dynamic torque sensor? Well, a rotary torque sensor will, in most of the cases, work with a torque analyzer, in this case here, a PTT, and the rotary sensor will come in between the tool that is applying the torque and the fastener, here the bit. So it will be really directly in line into the torque application. And this will give us, again, some insight on what is the torque currently applied on the assembly. Some differences with static torque measurement and static sensor are that static sensors have a strain gauge mounted on the shaft, and as the torsion is applied on the shaft, the resistance the resistance built in the circuit is going to measure the variation due to the torsion, due to the reaction, and then be able to send out what is the torque that was applied on the shaft. When we look at dynamic sensors, we have slip rings mounted on the shaft, and as torsion is applied on this shaft, the slip ring will move differently depending on this torsion applied on the shaft, and we will then be able to read the difference between each of the slip rings, then turning the analog signal into a digital torque reading. Torque sensors fall under different criteria: accuracy, standard, and calibration. And when we talk about accuracy, there are really two things to keep in mind. A torque sensor will have its own accuracy. So in terms of Mountz rotary torque sensors, it will be plus or minus 0.2% of the full scale. So this is as a standalone sensor. But as we seen just a few seconds ago, a torque sensor is going to work with a torque analyzer. And in this case, we have a torque measurement system. And this system itself has its own accuracy that we need to take into consideration. So in the example of Mountz tools, when we have a rotary torque sensor integrated and connected with our torque analyzer, the system accuracy will be plus or minus 0.5% of readings. And as you've heard, I talk about accuracy on full scale and accuracy of reading. So what's the difference between that? Plus or minus 0.2% of accuracy of full scale means that at 100 Newton meters, we will have an accuracy of plus or minus 0.2 Newton meters. And at 50 Newton meters, we will have an accuracy of plus or minus 0.2 Newton meters as well. So that means that throughout the range of the sensor, the accuracy remains the same. When we talk about accuracy of reading, then the accuracy will be variable depending on the torque read. So at 0.5% of 100 Newton meters, the accuracy will be plus or minus 0.5 Newton meters. And if we take into consideration 50 Newton meters, in this case, the system accuracy will be plus or minus 0.25 Newton meters. So again, the accuracy will vary depending on the torque that is being read by the system. Torque sensors, as any other sensors, need to be calibrated and certified. And for the calibration of torque sensors, the standard of calibration and certification will depend upon the country that the calibration laboratory is located in. As an example, in the UK, we will have the BS 7882 that regulates the calibration of sensors. In the US, it will be the ANSI Z 540. But something that is important here is that most of the calibration laboratories around the world for torque will follow the guidelines of the ISO 17025 norm, which is an internationally recognized regulation. In terms of calibration, some customers have intervals integrated into their QMS, quality management system. And in this case, they can, as an example, choose to calibrate their sensors every 6 or 12 months, so with time interval. Or sometimes customer may want to take into consideration the use of the sensor, so for how many cycles the sensor was used, and then determine this interval based on this information. So measuring dynamic torque sensor can be done around 3 phases related to the assembly. It can be done prior to the assembly, during the assembly, or after the assembly. So if we do it prior to the assembly, this generally will be happening in a laboratory or dedicated space to check the tools. So in this case, we will need the sensor mounted on the rundown adapters so that we simulate the assembly. So we will then calibrate and check the tool before sending it to production. After the assembly, we'll be basically running audits on the parts. So in this case, we will be able to check the torque left into the assembly. This can be done through different testing methods, one of them being, as an example, the marking method, where we will mark a point on the bolt and on the part and check as soon as we have the first rotation that we will then determine what is the torque that was at that time in the assembly. But the most common way to use rotary sensor is going to be during the assembly. So this offers different advantages. One of the main advantage is that in this case, the production tool, so the torque tool, is going to be checked in real production conditions on real parts. So what we do, as we've seen in the previous slide, is we mount the rotary sensor in between the tool and the bit, and then we are going to use the tool in real production, and then we will be able to see how the tool behaves under these conditions and then adjust it if necessary. Another advantage of doing that is, and that's important for some customers, is that we don't need to stop production to check what is the torque applied on the parts. So it means that the tool remains on the workstation and production just continues as usual. We just collect some fastening data during production. We can also use dynamic sensors, rotary sensors for R&D purposes. We know that torque can be determined theoretically through different formulas depending on the many different factors, but we also know that sometimes reality can be different from theory. And in this case, dynamic sensors can be used to either validate or redefine what is the target torque for a specific assembly. So what would be done generally in those cases is that we will fasten the fastener up to a yield point or to the breaking point even. We do that through different cycles for different rundowns. Each time a new fastener and a new hole, threaded or non-threaded, to match production realities. And once we have collected this information, we then have an average yield or breaking point, a torque value, and we would generally take 70 or 80% of this torque value so that we can then determine a target torque that will be roughly and reasonably accurate to keep the part assembled correctly. Rotary sensors can also be used for auditing. So in this case, this can be done for internal audits or external audit. So the aim here is to go and check that the production tool matches the quality requirements, the production requirements, or your own customers' requirements as well. So what we do here is we check the tool production reality. So this is during production most of the time. We then collect the data and save them onto the torque analyzer, save them onto the network and our computer. And this will help limit the exposure, as we will be able to check if the tool matches those requirements. If not, take the corrective actions to ensure that this is the case. And it limits exposures again against quality issues, as the tool is regularly checked, making sure that the quality on the assembly line is properly respected. The frequency at which this needs to be done is going to depend on the quality management systems in place into the factory, but it can also be guided by the results of this auditing. Typically, when we see that a tool remains calibrated, remains repeatable each time we audit it, we could then eventually consider increasing the time between the interval, the auditing intervals. But on the other hand, if we see that the tool is deviating, is not calibrated anymore, and is not in line with the requirements anymore, we can then increase the frequency of the auditing intervals so that we can again increase the quality of the production line. When we look at rotary sensors, there are three main types of sensor. We have the brush sensors, brushless sensors, and torque and angle sensors. So the brush sensors are going to be used very widely among the industry. These are sensors that will have all the features we've been talking about. And the difference with brushless sensor is that brushless, as its name indicates is roughly and basically contactless. And these brushless sensors will be able to sustain more and longer working periods. So brushless sensors will be the type of sensors indicated for, as an example, spindle checking. So where the sensor is mounted into a robot on a 24/7 3-shift production line. So the sensor remains on the tool and constantly check what is the torque of the tool for each fastening. So brushless sensor will be able to sustain very heavy production conditions. Torque and angle sensors will be indicated mostly for auditing purposes. So for first movement test, as an example, where we will be able to detect as soon as the fastener moves. So then determining the residual torque, so the torque at the assembly after the assembly was done. We can also use torque and angle sensors for checking tools used for torque plus angle strategies, so that we know that the tool respects those criteria again. So now that we've gone through the theory, let's have a look at how those tools work in reality. So with us today here, we have a LTT torque analyzer. So this torque analyzer works exactly the same way as the PTT that was shown earlier. The only difference is that we have here a built-in static sensor. So for the demonstration purposes, we have the LTT connected on the left to a rotary sensor that I have here. So this rotary sensor is a brush sensor with a torque range from 1 to 11 Newton meters. We also have different tools that we will be used for the demonstration. One of them being an HF 100 torque screwdriver. So this torque screwdriver is a clutch tool on which we can set the torque by turning the ring here clockwise or counterclockwise. And this tool works with a transformer that is just out of the window here. So if we start by looking at the LTT, and I want to start today with showing the difference between static measurement values and dynamic values. So to do that, I'm going to use this HF 100 electric screwdriver onto the static sensor. And of course, I need to make sure that I use the proper accessories for that. So I'm going to use a round down adapter here with the proper bit. So I'm going to mount this here in the bit holder. And we can then go ahead and make some measurements. So we see 2.35 Newton meters, 2.2 Newton meters, so we see that on the static sensor, we achieve a torque around 2.2 Newton meters. So now let's move to the static sensor. So to do that, I'm going to the dynamic sensor, sorry. So to do that, I'm going to mount the dynamic sensor into the bit holder here and use the screw plate to make the readings. So I have here the LTT screen with the dynamic sensor. So I need to indicate the entity which sensor to consider. So it recognizes the rotary sensor, RTSX 100i, and I'm then ready to make some measurement. So let's go ahead. What we see here is that the values with the rotary sensors are basically higher than with the the static sensor. So we see that there is a difference between both type of measurements. So the reason why it's important is that we want to know what is the torque really applied on the part, and this dynamic sensor will help us with that. Now, let's make another test. I'm going to change the rotation speed on the tool. So to do that, I can use the screen here. So I'm now at 150 RPM, and I can increase it to 550 RPM. And let's see what are the results. So by increasing the speed, we can see that the torque values are now lower than with a slower speed. And this, again, as mentioned before, is a variable having a very strong influence on the torque delivery and the torque applied on the sensor and on the fastening, on the fastener. So it's important, again, to check the tool in real conditions. So a good thing with the LTT is that we can also take graphs to see what's happening during the assembly. So we can go ahead and start the graphing function here. And I will be able to zoom in later on. So if we decide to zoom here, we can see let's go again and make a new one. So with the graph function, we can see what's happening in real time onto the assembly, and we can then determine if the tool is behaving as it's supposed to be. Now that we've seen an electric tool with a dynamic sensor, there are tools that come already equipped with a torque sensor, and it's the transistorized power tools. So for today's demonstration purposes, I have with me an ECTD controller and this ECT tool. So these tools are transistorized tools, and they would be basically built with an integrated torque dynamic sensor directly built into the tool. So we have now on the screen the ECTD controller screen. So we have our target torque of 2 Newton meters, and we also have our LTT ready to measure. So let me switch back to peak mode here. And as for the HF100, I'm going to mount the dynamic sensor between the tool and the bit. I'm going ahead and making a fastening. So we can see that the results are quite consistent between this dynamic sensor that is used in line with LTT and the dynamic sensor that is used also into the tool itself. But the transistorized tools also offer some other possibilities, such as graphing possibilities. And if we look at them now, we have the graphing function here. So we can set 2 different channels. So torque, we can also have speed in this example. So if I go ahead and make a graph, we'll be able to then determine what's happening during the assembly. So in this case, in blue, we have the torque, and in red, we have the speed. So we can see that when the tool reaches the setting point, the speed slows down until we reach the target torque of 2 Newton meters, where the tool stops. So having the possibility to see graphs directly from the tool itself is going to be important for, again, quality purposes, as it will be able to, you will be able to determine if something is wrong during the assembly, what and where is it going wrong. It can also help set the tool in terms of angle windows, or also set the speed of the tool to really help increase productivity and improve quality as well. So at this time, what I would like to do is open the floor for questions. So feel free to write your questions in the chat. Jody, who is here with us today, will be happy to read those questions, and I would be happy to answer them. Jody, do we have any questions?
Thank you, Adrian. We do have some questions. The first one is, what is the recommended number of rundowns to have an accurate overview of the calibration of the tool?
Yes, that's a good question. Every company will have different answers here. Our recommendation would be to have at least 25 rundown to really have a good overview of how the tool behaves and to be able to get some accurate statistics out of those rundowns. And something that's important, and that's true with all type of torque tools, is we need to make sure to exercise the tool before we start taking the measurement. So typically we would make 5 or 10 fastening with the tool before we start checking those rundown and keeping them in memory for the statistic purposes. Any other question, Jody?
We do. Another question we have is, do the tools offer a memory feature to save the data?
Yes, they do. So the LTT and PTT offer some memory features where we will be able to set some programs, testing programs dedicated to each of the tools. And we can also store the measurement data into their internal memory and then download them to the computer. And the same goes with the ECT and ECTD tools, where we have integrated memory and integrated SD card as well. So in this case, we are going to save every fastening data onto the tool. So keeping really traceability with the tool, and we can also link this information to barcode, screw counting, and different features that are really related to those DC control tools.
And the next question we've had in is, does the rotary sensor work with air tools?
Yes, they do. So in air tools, we have mostly two types of air tools. There are the air screwdrivers. So the air screwdrivers can be used with brushed and brushless sensors. And there are also the hydro-automatic tools, so the pulse tools. And in this case, what is recommended is to use brushless tools, as brushes may sometimes create some bounces that will generate some false reading. So with pulse tools, what is recommended is to use brushless rotary sensors.
Great, and that is all the questions we have. Thank you, Adrian.
Great. Well, thank you very much, everyone, for joining us this morning, this afternoon, or this evening for some of you. It's always a pleasure to have you, and we are looking forward to see you next time. Have a nice day, everyone. Bye-bye.